So now that we've seen a handful of strategies for integrating, in this section it's good to look at a general strategy that we can apply to any integral and try and decide what would be the best strategy for solving that integral. So here, that's the goal of this section. And here's just a broad overview of some of the antiderivative formulas that we've learned so far. You can see it includes almost everything that we've just sort of memorized at this point. In other words, these are all the integration formulas that we've mostly just have learned and have memorized, so that our goal would then be to try and manipulate some function into one of these known forms in some way or another. And the goal of integration by parts, for instance, was to manipulate an integral into a form where it resembled one of these, where we have a known formula for integrating. Or similarly with trig integrals or trig substitution, or even what we did in 7.4 with partial fractions. All of those techniques that we learned were just techniques for manipulating the integral into one of these forms that we can integrate. And the first step is usually to simplify the integrand if it is at all possible. One thing we can always look out for are obvious algebraic maneuvers to simplify. For instance, here I can easily distribute the square root of x. And once I do that, then it's in a form that's very easy to evaluate, right? Or here I can simply FOIL this expression. And after doing that, then it appears that there are other identities that we can use. For instance, we know that sine squared plus cosine squared is equal to 1. We even know that 2 sine x cosine x is a double angle formula for sine. So actually, that can also be simplified down to just sine of 2x. And then from there, it's actually in a form now that's ready to be integrated. Second step would be to look for an obvious substitution. And usually the general thing that makes it obvious is if I look at a function that can be replaced, where the derivative of that function is present somewhere, or a multiple of the derivative is present somewhere else. Take, for instance, here, x squared minus 1 would be an obvious substitution, because if I take that to be u, then its derivative is a multiple of the x that we have in the numerator. Right? So we get a multiple of the x in the numerator. So this becomes an obvious substitution that transforms this into a form that we can easily then integrate. So we would have a 1/2 integral 1 over u du. And then once we've done those two maneuvers, then we can try and classify the integrand according to its form. And this might clue us into some other technique that would be useful for evaluating the integral. And in this case, we have some strategies for dealing with trigonometric functions. Those are kind of the basic strategies that we had in section 7.2, where we used certain identities to manipulate the integral in certain cases. When we have rational functions, we can think about the partial fractions that we did in 7.4. If we notice there's a product in our integral, then we can think about using integration by parts. And usually with integration by parts, it will involve some sort of product of something that will simplify when we take its derivative. And that's how we know that integration by parts will be a good choice. And one other thing to look out for are radicals, right? And we saw in the last section that we can substitute a radical expression when we want to use what's called a rationalizing substitution. So that's one thing to look out for. And another thing to look out for are the forms where we can use a trigonometric substitution. So those are the radicals of the form x squared minus a squared, or x squared plus a squared, or a squared minus x squared, where we know that substituting a trig function will allow us to simplify it with trig identities. Okay, so after we've gone through all of that, then one last thing we can do is try something else, right? Suppose we went through all that and we didn't get anywhere. Well, we can try a substitution, something maybe different than what we've tried in the past. Try something tricky, for instance. We could try integration by parts, even though maybe it's not obvious how we're going to set up the parts. We can think about being a little bit more creative with how we choose the u and the dv. But most likely those are going to be after you've kind of gone through and tried some of the other strategies first. Okay. And then one last thing here is to think about manipulating the integrand. So algebraic manipulations in particular can be useful, and also thinking about using trig identities also may be a useful trick. So one thing I notice here in this example, 1 minus cosine x can be transformed using 1 plus cosine x, sort of like the conjugate, right? If I think of this as something that can be multiplied by 1 plus cosine x, well, let's see how that would transform it if I multiply 1 plus cosine x over 1 plus cosine x here, so we're not actually changing the value. Then I have the integral of 1 plus cosine x in the numerator, and then this becomes, when I multiply this out, 1 minus cosine squared. And then we know that 1 minus cosine squared is really equal to sine squared. So actually we've done a little bit of manipulating here to get it into a form. We're now looking at it, what might not be obvious now is what to do from here. But what I notice is that you could, for instance, split up the terms, sort of thinking about what sort of algebraic maneuvers we have to try. And then the first term here would be the same as cosecant squared. And that's actually one where we know what its antiderivative is. That would be negative cotangent. How about cosine x over sine squared? I think this would be the same as cosine x over sine, which is cotangent, times 1 over sine, which is cosecant. Okay, and that's actually also another one that I know the antiderivative of. That's the derivative of cosecant, or negative cosecant. So from here we can get the answer. So this would be negative cotangent minus cosecant. So one final thing to think about here is also how to relate the problem to previous problems. So once we've kind of had some experience with all these different techniques, we may start to recognize patterns or recognize how these strategies can be applied in other situations. So let's try this example here and see where our experience will take us. One thing I remember is that we can try this trick where if I take tan squared, I know that's the same as secant squared minus 1. And then distributing the secant, I get secant cubed minus secant. Now this may seem difficult now because I've got the integral of secant cubed minus the integral of secant. But the nice thing is we've encountered both of these integrals already. Back in section 7.2 we saw how to integrate secant cubed. Now it wasn't an easy integral, but we were able to do it. So now we can look back at our experience doing that and just save ourselves now the hassle of having to do this one from scratch because we've worked that one out already. If you remember, it was something like 1/2 secant x tangent x plus 1/2 ln of secant x plus tangent x. And you can look back at the details of how we did that, but it was somewhat complicated because it involved using integration by parts and some tricky manipulation. Similarly with secant of x, we know that was equal to ln of the integral of secant x was equal to ln of the absolute value of secant x plus tangent x. And so combining these guys, we would have the integral of our original thing becomes the integral, or becomes 1/2 secant x tangent x minus 1/2 ln of secant x plus tangent x. And so there we were using the experience that we had with secant cubed to save ourselves the hassle of having to do this one from scratch. So you can see the notes from section 7.2 to see how we got the integral of secant cubed. And one other thing is to also consider using several methods. In other words, maybe doing substitutions mixed with integration by parts is something that you might come across every once in a while. Let's take this example, tan cubed over cosine cubed. As it is, I'm not exactly sure what the antiderivative is, but we can try a little bit of simplifying or manipulating. For instance, if I try and rewrite everything in terms of sine or cosine, oftentimes that can be a helpful way to manipulate it. For this one here, I think tan cubed, I can write that as sine cubed over cosine cubed. And then I have another cosine cubed down here. So that would be sine cubed over cosine to the 6th. I know a strategy for dealing with odd powers of sine or cosine, so maybe that strategy will work here. Because I can take a factor of sine, save that for a substitution. Sine squared can then be rewritten in terms of cosine. 1 minus cosine squared. And then, oh yeah, so we're saving the sine. So then I can let u equal to cosine x. So du is negative sine x. So this becomes the negative integral of 1 minus u squared over u to the 6th du. Okay. And actually looking at it now, it's not so bad. I can split up the terms. So I got 1 over u to the 6th is u to the negative 6. Minus u squared over u to the 6th would be u to the negative 4. So this integral could be easily done now. So it'll be, let's see, u to the negative 6 when I integrate will be negative 1 over 5 u to the negative 5. And then this will be negative 1 over 3, so plus 1 over 3 u to the negative 3. and then we can put the values back in. So this is 1 over 5 times cosine to the 5th minus 1 over 3 cosine to the 3rd. Okay. Or I can also write it as 1/5 secant to the 5th minus 1/3 secant to the 3rd.